December 20th, 2019. The naive School of Physics is out for the semester. I wound it up a couple of days ago on Monday, and here we are, Friday, the first time during the holiday shutdown of the school. But I still will be talking about things a couple of days a week here. The reduced schedules here for describing mock matter. The holiday physics retreat. Mondays and Fridays, 20 hours, GMT. And I'm going to be showing you a bunch of glass beads today. And the pyramidal cube theory forms beads into pyramids and cubes. Some reading material is fun. The Glass Bead Game by Hermann Hesse. It's about Magister Ludi. That's the person's name. An expert in putting beads together. I don't know if it was 1960, but I read that around 1968, I think. So that's a good one. So here's a picture of carbon in the upper right. And I'm going to be putting together a bunch of these little pieces like that there. Hello, back over to the laboratory here, the Maui Theoretical Physics Laboratory. And here's the bucket of 57 nucleons that I was working on a couple of weeks ago. And this one showed that just randomly trying to make an iron nucleus out of styrofoam balls will indicate a random shape, but it also shows that these white protons form lines of white protons at random. No matter how many times you randomize it, it always comes out the same. White touching white. Protons have to touch protons in stable elements of the nuclei. So I have a bunch of these models here. Of course, the famous cube is shown here for iron. And it makes a transition from a two-layer cube into a four-layer cube for iron. So I'm going to show this a close-up really soon now. So this is kind of an informal seminar, or what did I call it here? The Holiday Physics Retreat. And we're making a mockery of matter, but never a mockery of physics. This is a very serious thing here. So I'll zoom in on this here. And then I can hold up pieces right in front of the camera showing how things are starting to get put together here just to form hydrogen and helium. All right, so here's the hydrogen parts. We have the proton in white, and there it is, the element hydrogen, and deuterium has a brown and white. So that was easy. Now lithium has 3 protons, and it forms lines of protons. So I put together this lithium-5 isotope as a little pyramid, and then that would get connected onto a cube to make iron. And then you see a line starts to form for iron, and it finally will make a ring. Later on, you'll see that coming up. But part of the excitement today is that I'm starting to make a mock-up of the nitrogen nucleus. So nitrogen is a little bit bigger than carbon. So there's carbon with its 4 protons at the extremes. the other 2 protons are in the cube in the center, just like the 2 electrons in the center of the atom in the S shell. So, as above, so below. I think I have a model of nitrogen laying around here someplace. Oh, here's another carbon. No, this is a chunk of oxygen. I sure have a lot of these carbons. Oh, I see what happened. There's nitrogen. And we see that for nitrogen, first we have to get 7 protons. And here you see there's 6. For carbon, that means we have to add 1 proton and 1 neutron on the 2 faces. So there goes 1 proton on one face, and that will hit the neutron on the other face. And then we get nitrogen. Now, as we look at nitrogen a little closer, we see that there's 3 protons at the extreme ends here. And this is something that I'm emphasizing in today's workshop. The retreat, the physics retreat today. See how nitrogen has 3 protons sticking out there, unlike other elements? Well, in the molecule of nitrogen, there's 3 bonds. And I speculate that that's because there's 3 protons in the extreme positions here. So that's also being modeled in Blender. Let me show you a file that's available for the computer-aided design of nitrogen. Okay, I've gone over to computer screens. So instead of just styrofoam balls, I also can use simulated spheres. Over in the Thingiverse here, thingiverse.com, you can see I've got radon on the top left and oganesson on the top left there. And then below that's polonium. The charge distribution is shown there with the white protons and blue neutrons. And then on the right you see there's some modules. I'm putting integer geometric modules available to make all 118 elements. And then below this is some smaller elements including nitrogen. Oh, there it is on the right. The nitrogen nucleus, and I have another close-up of that available here. There it is, just like I was showing you on the styrofoam. There's 3 of these protons, and if you look at the chemistry books, they'll show the nitrogen molecule N2 has 3 bonds between the 2 atoms. And that's what I'm going to be showing today in more detail, is that I can put together a mock-up using a steel springy tape measure to show some accuracy of how the nitrogen bond works. And I have 2 turntables I'm going to use where I can rotate each of them, and the springy tape measure will wrap around each other, forming a bond. And as I move the apparatus away from each other, there will be a force bringing them back. But if I move them too close together, you'll see that these springy bonds make it come apart, so that there's a balance point of the atomic scale of the bond for nitrogen. So as a mock-up, this is somewhat using the Blender type of thing that I've shown before, and I'm bringing that up now. Blender 3D version 2.81. I'm going to load a file here. All right, so I'll just aim this a little better. This is the Blender file for a neutron at the top left, a proton at the left, and an electron on the right. And those three things in the middle is the bond. There's 3 dimensions in the bond. This one here is a time-like dimension on the bottom. And I can select each one and move them around. See, there's the time-like dimension I can move out of the way. And here's the 2 space-like dimensions. I can bring them down so they're not blocking the view as much. And they're flat. And now on the right here is electron. And let's take a closer look at that. Oh, let's see, I can select it and then rotate it. Pretty soon it's going to start rotating. Except I have to select it again here. Oh, there it is, the rotation bar. So with Blender 3D, you can see the electron has 3 dimensions of importance. 1 dimension is coming out of the electron, and 2 dimensions are going into the electron. So there's these 2 space-like dimensions there at the top, which is from the proton. And then it returns an equal amount of the adding those together to the proton. So it's a flow back and forth that the proton sends out time, and the electron. Oh, let me start over again on that phrase. Okay, the electron here has an outcoming time-like dimension that goes over towards the proton. And I'll just move that up here. There's that dimension. See, it comes out of the electron and it goes across towards the proton there. Now let's take a look at the proton closer, though. So we see it has 2 dimensions coming out, and then there's one hole there going in, and on the top there's another one coming out that goes to the neutron. So there's the neutron up there, and that receives 1 dimension to keep it alive from the proton down here. Now the relationship between the proton and this electron over here on the right is that the 2 space dimensions get added together. So it's a linear addition going on here in the electron. It then returns the sum of those 2. So the amount of time-like dimension coming out of the electron is equal to the sum of the magnitudes of the space-like dimensions going in. Those 2 dimensions here. All right, so now we're going to go back to a few more words of the mock matter considerations during this physics retreat. And the pyramidal cube theory is going to be using the electron and proton and neutron models that you just saw. And it's useful to put together glass bead models, and so the physicist can rotate the model around in one's hand and observe it using geometric reasoning. And then these are kind of like games for the Christmas season here, where the green glass beads in this picture we could pretend are protons, and the white ones, clear, would be the neutrons. And then at the top you see the iron, And in the bottom is a bunch of small pyramids. There's a 4-layer pyramid at the bottom. And then there's a cube above that, a 3-layer cube for iron. Iron's where the elements make a transition from 2-layer cube to a 3-layer cube. And see, here we see that this is enough for making a model of germanium. So with the 3-layer cubes available, we could make the element germanium with this. I'm going to let you look at a video right now as I set up the camera for something coming up real soon. Hello, today I'll be talking about the cube at the center of the iron nucleus, and the cubes in carbon through uranium, and it's very common. So there's a couple of things that happened at first during the year 2015. I put together a random collection of 32 protons and neutrons, and I was never really satisfied that iron could be modeled this way. I had selected iron because of its amazing magnetic properties. Now, to evaluate the theory of the cube, I did this in 2017, and it was a static theory that the nucleus would be a stack of protons and neutrons, and not chaotic and not dynamic, just based on a cube. And it turns out that there was a easy way to calculate something for this iron 57 cube. Iron has two common isotopes like 56 or 57 protons and neutrons. That's called A, the mass number. And then Z is the number of protons, 26. And we see that when you use a cube theory, these integers work out very well for these groups of numbers, where 57, the number of protons and neutrons in iron, is 27 plus 6 times 5. A cube has 6 faces. So on each face of the cube, we would have 5 protons and neutrons. And the Z is 26, which is 8 in the cube, and 6 times 3, because the cube has 8 corners and 6 faces. So on each face, there would be 3 protons. And it turns out that this is similar to lithium, where lithium is rare in the sun, but iron is 10 million times more abundant. Apparently, lithium has been absorbed by these cubes, producing iron. Now, another point I wanted to raise on this is that I wrote a paper last year called Ferromagnetism from Iron's Nuclear Structure. And it has this face-armored cubic lattice, so that there's a certain crystallographic type of lattice for this. And I've found that the cube 2 by 2 by 2 is stable, but not 4 by 4 by 4. So this is because the 4s have, at the center of the cube is a vacuum. And also the 2 by 2 cube is, a vacuum is at the center of this. For example, here's the model. You see there's 2 protons there in white, and just like there's a 2s orbital at the core of atoms. So I'm pretty much certain that there is a cube at the center of iron because of all the evidence that I've found. Let me try to tell you about a quick list of the evidence I found for this, and that technetium is lightweight, cerium and iron spark when struck. And you can just read a bunch of these bits of evidence here. And but I'm also going to show you a couple of nuclei. So we can see over here the gadolinium nucleus right here. It's much bigger than iron right here. And you see they both have this pyramidal cube structure that results in a ring, 2 rings of protons. And the same for gadolinium. This gives me certainty that this is the correct theory. Other elements are not like this. I evaluated all the elements, 118 on the periodic table, and only gadolinium, cobalt, nickel, and iron have these 2 coaxial loops. So that I'm very certain about this. So here's the famous cube 3 by 3 by 3. There's a proton at each corner. And thank you very much for listening. My name is Alan Falmsby. Well, that was enough time for me to set up the Christmas scene here. I'm going to open up prematurely some presents. I'm going to make a mock-up of nitrogen. The nitrogen is going to have a turntable. So on this, I'm going to have a wheel, and I bought a couple of wheels for the turntable here. Let's see, take this wrapping off the gift here. Oh, that's why I brought my tools along for the unwrapping gifts here in the future. This is future gifts for future science. And this wheel then has nice ball bearings on it. And I'll be making a turntable on the bottom of the nitrogen molecule. And then I have a second wheel here that I have to open up. This is the dangerous part of the holidays, unwrapping this excellent plastic wrapping. High quality containership here. It's another 6-inch steel wheel for the top turntable. So I'm going to be suspending some tape as the bond. The nitrogen bonds are going to be represented as tape. Measuring tape. A tape measure. That's what this is. I bought this steel tape measure, 100 feet. And I'm going to cut chunks off the tape. And each of those will be from 1 proton to 1 electron. Electrons will be a piece of lead or something, or maybe, and then I'll spin the whole thing around so that the tapes get wrapped up in each other on the top and bottom wheels. Now, gravity's going to be holding on to one of them. Now, here's the hard part. It's opening up the tape measure. This has the very highest quality plastic. And don't do this at home. Have a qualified physicist take these measuring apparatus out of the wrapper. It's only made of steel, though. I'm not sure how this is going to end up. I don't have any magnets here. It wouldn't be safe to have a steel tape measure. The Christmas season can be full of joy. As you see the gifts under the tree. And then the child could open this. But you never really have a child nearby when you need one. All right. There's the tape measure. I'm going to get a zoom in on this with the camera. Stand by for a minute. Steel tape. It's springy. So there it is, the one bond of a two-dimensional structure. It's flat, just like I was saying. The electron and proton are paired together using two space dimensions. So that's the flatness. I can't turn it left and right very easily because those two dimensions are connecting the electron to the proton. But I am able to move it in the third dimension very easily with no resistance, no interaction between the proton and the electron in that dimension. Also, superconductivity becomes possible when many of these layers stack up. They're very thin, so an unlimited number of these layers can stack up on top of each other in a circuit as the bonding pair overlap each other from different atoms. So what I'm going to do is cut this tape apart. I'll take a chunk of this and cut it. Or I'm attempting to cut it, but it's made out of steel, so I have to groan while I'm doing it. All right, the cutting experiment was a success, and the steel was not cut. So I'm going to continue this next Monday at 20 hours Greenwich Mean Time, and at that time I'll be having a flywheel on the bottom, not a flywheel, a turntable on the bottom, a turntable hanging the tapes from the top. And then the bottom one will have rigid rods on it for 3 bonds, and the top turntable will have 3 tapes for flexible bonds, and they will wrap around the rods on the bottom, and they will turn back and forth, and that's the plan. All right, so I'm going to wind up now. Stand by. Okay, I'm back at the control panel now. Oh yes, there I am at the control panel. And oh yeah, that reminds me, I want to show you a little more Blender 3D. Okay, we're back to the Blender 3D picture here. And this is the neutron, the top left, the proton below that, and the electron on the bottom right here. So I can select that whole thing and rotate it around for you. So I'll turn it this way so you can see the bottom part. So the proton's on the right and the electron's on the left now. And these 3 things between are those 3 dimensions of the bond. So it's a flux. So at different levels, it's a flux like magnetic flux or amperes of current is a flux, or a length of a velocity is a flux. So I'll just select this again and see what I can do about rotating this thing here. RR. That didn't work. All right, so I'll just rotate it with this thing. All right, so I'm going to select it again here on Blender, and then go to this rotation deal here and bring it back into some kind of shape. All right, I hope you enjoyed that little half hour here during the holidays. And I'm just going to have a bit of a goodbye message here about the fun and games we've enjoyed. I've already unwrapped these gifts for you of the last week. The replenishment power. Gravity, even in the cold, is replenishing the atoms and ions. So it must be hard to get to absolute zero when gravity is replenishing every proton-electron pair. Let's see, Merry Christmas. The flat subuniverses are described for a molecule. It's kind of like this picture here. You got the flat subuniverse of one proton and one electron. From the electron's point of view, the sky is just a ribbon because it's two-dimensional. And the foundation has been laid for physics now below energy for the finest reality that I can portray for you. The conservation of energy is true. It's a lumped functional model that does not say that it's really 6 powers of dimensions. Meters to the 4th power divided by seconds to the 2nd power. So that's going to be affecting the chemistry very much. Because chemistry is largely analyzed through energy conservation and use of potential energies and kinetic energies. And also there's another school of thought for chemistry where the charge distribution rules are very important. So my discoveries of the nucleus are very helpful there. Now the mock-up of the nitrogen molecule is getting started now with steel tapes for bonds. And then you can see more of this on the ContraSpline website page at impuremath.wordpress.com. Thanks a lot. Bye.